Good afternoon. My name is Robert Randall, and I'm a Senior Optimization Specialist at Constraint Consultants. Today, my colleague Herb Lustig and I are going to discuss work we did for Birchbox on why formulation matters and the reciprocating integer programming technique that we used. This work was performed by Patricia, Herb, and myself for Birchbox. Birchbox is an online monthly subscription service that sends customers a box of beauty supply samples. This is a $7.5 billion market. Since launching in 2010, they've grown into a leading monthly subscription service with over 1 million subscribers and 2.5 million active customers. They currently partner with over 800 brands to send monthly boxes to subscribers with a tailored set of beauty or grooming samples based on the subscriber's preferences. Birchbox is a custom clustering application that takes the 1 million unique subscribers and, based on subscriber profiles, history, and other attributes, groups them into a significantly smaller number that can be fed into the optimization models. Birchbox approached Princeton with an already built MIP that used the Gurobi solver to optimize the box creation for that smaller group of similar subscribers using some proprietary objectives and constraints. As is often the case, the model worked well initially, but as the customer base grew and with increased offerings, the model did not scale well. The model was often taking days to solve, which caused issues for operations as the model would run up against production deadlines, and that prevented Birchbox from testing alternate plans, and they could not improve the box experience for their subscribers, as the model is not able to handle having any new information added to it. At a high level, let's describe the problem to allow us to talk about the differences between the models. To start, there's a set of products that go into the boxes. There are roughly 100 different products that are available each month to go into the box. Each product has a set of attributes associated with it. This includes things like weight, volume, value to a subscriber, and the maximum inventory for that product. For each product, there may also be a minimum number that need to be sent out to the subscribers per month. This could exist because the inventory for that product is too high. Each month, Birchbox's machine learning algorithms group subscribers into clusters. This gives the optimization model between 2,000 and 5,000 clusters of subscribers to solve for, instead of trying to solve for the full 1 million unique subscribers. There is an eligibility matrix for each subscriber cluster and product pair. A subscriber either must receive the product, can receive the product, or must not receive the product. This is an input to the optimization model based on business rules that Birchbox has in place. The first goal of the model is to create box configurations. To build a box configuration, we take the available group of products, feed that potential product set through the constraints to make sure that they can be grouped together in a box. Example constraints are things like the range of products in a box must be at least 5, but not more than 7. There are maximum weight and volume of the products in the configuration. The output is a valid box configuration. The next step is to assign the configuration to subscribers. To use a box configuration, it must be assigned to a minimum number of subscribers, but no more than a maximum number of subscribers. Each subscriber must be assigned to a box configuration by the model. One key component that Birchbox wanted was the ability to identify quickly if it is not possible to assign each subscriber a box configuration because of lack of inventory or because of eligibility. One of the pain points with their initial model was that it could run for multiple days, and then when it solved, they would find out that each subscriber was not assigned to a box configuration, which meant Birchbox had to go back and work out figuring whether the inventory they needed to add or if there was eligibility they needed to update. Birchbox's goal is to use a small number of box configurations, as each configuration that is built adds to the production cost for the month. In doing this, the model needs to respect all product maximum inventory and subscriber eligibility, which is a key component in the box experience for subscribers. At this point, I will turn it over to Irv to discuss the new algorithm that we created to solve this problem.
Thanks, Rob. I'd now like to start by discussing the notation we use in the problem. First, we have P as a set of products, S as a set of subscribers, and B as a set of box configurations. There's a set of attributes that exist for all the products, such as weight and volume. And for each one of the products, the mu values indicate how much weight or volume, etc., contributes to that product. We have a set S hat P that corresponds for each product to the set of subscribers that must receive that product, and the converse set for each subscriber of the set of products that subscriber must receive. The converse of that is the set of subscribers for each product that cannot receive that product, and for each subscriber, which products that subscriber cannot receive. Then there's a bunch of other parameters that are provided, which include the number of subscribers per box, which has a minimum and maximum. That's global across all the boxes. A number of different box configurations. So we want to make sure we have a certain minimum and up to a certain number of maximum number of boxes configurations that we create. The number of products per box is something like typically numbers 5 and 7, how many products we put in a box. Then there's a total product quantity across subscribers. This is a soft minimum. You want to make sure you send each product to a certain number of subscribers, and then there's a maximum inventory of each of those products. There's a total attribute value, which is going to be for each attribute, defines the minimum and maximum of that attribute per box. The key concept is pattern generation for each subscriber. Given a subscriber, we know which products that subscriber must receive and not receive. We create a vector of binary variables indicating whether the products will be in that box configuration. The constraints are for each attribute. We sum up how much times that attribute contributes from that product and make sure it's between a minimum and maximum. And then we have to limit the number of total products that we receive. The objective function will be based on what are called duals in quotes, and we'll describe that momentarily. When we solve this simple MIP, we get a feasible new box that corresponds to which products can fit inside that box as a pattern. And that then gives us the set P bar B, which is for each box that we've created, which products are in that box. We then add a constraint that restricts that pattern from being generated again. And this will be, we keep adding these constraints as we generate new patterns. We also check for that box which subscribers are actually eligible to receive that box. The original MIP problem formulation had a lot of variables. It had a binary variable and a quantity variable indicating whether the product fit in the box. It also had a binary variable for whether each subscriber would be assigned to that box. So the dimensionality of the problem was based upon the maximum number of boxes you would create, but each product could go in each box, so that was number of products times number of boxes, and each subscriber can also go into each box. There's also a lot of symmetry. Boxes are kind of all the same and don't differentiate among each other, making the original formulation difficult to solve. Our master problem that we will create will be based upon generating these patterns. Once we generate these patterns, we now can color in for each box that we generate which products are in that box and which subscribers are eligible to receive that box. This reduces the total number of variables. On the other hand, we won't have a maximum number of configurations. Think of these configurations as going on as all possible configurations, and then we'll restrict which ones we actually look at. So the master MIP problem then has these decision variables. The QPV variables indicate how many times that product is used in that box, but only if the product is in the box. The ZP variables represent how well we're satisfying the minimum requirements for that product across all boxes. The YB and NB variables corresponding to whether the box is used and the number of times it's used. And the WSB variables indicate whether a subscriber is assigned to a box. But again, those variables are only created when a subscriber is eligible to receive that box. The QPV variables are only created from the pattern we generate when the product is actually in that box. Now let's turn to our set of constraints. The first set of constraints are Z variables, which we'll talk about later in a constraint, are constrained to be the maximum number that we can put in the products we can use. The Q variables are also constrained by that variable, but only if we choose to use that box configuration. The n variables are equated now to indicate that they are equal to the number of times the product goes in the box. And the n variables are controlled by the binary variables y, which indicate that we must send that box configuration at least to a certain number of subscribers, but up to a maximum number. The next set of constraints correspond to box and product quantities. Here we have an upper bound on the number of box configurations we can use. We're going to call that the hard option. We'll have a soft option where we don't use that constraint. The next constraint says for every product, we want to make sure that the number of times we use that product meets the minimum, but here's where we have the ZP, which is the error in satisfying that constraint. On the maximum side, that's a hard constraint. Again, we do this the same sum and say it must be less or equal to the maximum. We also connect the Q variables with the N variables based upon the number of times we're allowed to use the products in the box. So if we have here only 5 or up to 7 products in the box, then we know that the Q variables going across the products is constrained by the total number of products in the box and how many times we assign that to a subscriber. And then we also must build a certain minimum number of box configurations. The next set of constraints are the subscriber constraints. What we do here is the number of times we use that box configuration is equal to the number of subscribers that are assigned to it. And then for every subscriber, we then want to make sure that we use up to 1 box configuration. Note that we don't use equality here because equality might make the problem infeasible, as it may not be possible due to the inventory and eligibility requirements to assign every subscriber a box. Our objective function is first to maximize the number of subscribers assigned to a box. After we accomplish that, we do this hierarchically. We then look to, if we're using the soft option, to minimize the number of box configurations we use, looking to hit the target tau u. Remember, with the hard option, that was an explicit constraint. And the final constraint looks to minimize the error in satisfying the product minimums, where we weight that by the product maximums. Our new formulation now has a large master problem with lots and lots and lots of possible patterns, and that's probably very large. But we're going to address this via column generation techniques. We're going to generate the patterns as we need them and form a restricted master problem. This is not true column generation because every time we generate a new pattern, we add variables and we also add constraints. It's not branch and price, which require us to do branching in an LP kind of way. You can think of it as almost price and branch. We generate a bunch of patterns, solve a problem, get some dual variables, and then do branching by returning back to the MIP. This is it. I want to note here that this is column and constraint generation. So what do we mean by that? Every time we generate a new pattern, we add variables to our problem. That's just like in column generation schemes. But we also add constraints because each new pattern induces constraints that connect the Q and Y variables, the Q and N variables here, as well as the subscriber variables that are now new get connected to the N variables. So these constraints get added each time. So you can't use a classic column generation framework because each time the dimensionality is growing in the columns and it's growing in the number of rows. We call our technique reciprocating integer programming, or RIP. The idea here is that we're going to use MIP, or mixed integer programming, to solve both the mixed restricted master problem and the MIP pattern generation subproblem. They reciprocate by passing information back and forth. The restricted master problem generates duals that are used by the MIP pattern generation subproblem to create new patterns, and creates patterns that are then passed to the restricted master problem. To generate the patterns, we solve a MIP. We don't use any kind of heuristic or other way. We just solve a MIP, adding those constraints that restrict patterns from being regenerated. And then for the restricted master problem, first we solve a linear program and see that we can get every subscriber a box. Then we move and solve the MIP version of that problem. The restricted master problem is generating duals, either in the LP case, but it's also generating duals, and we say those with quotes. They're kind of surrogate duals that are used when we solve the restricted master as a MIP. So now let's talk about the different steps of the RIP algorithm. The first step is the Bootstrap step, which is where we generate the initial patterns that are needed. We do this by solving a pattern generation MIP, first generating the feasible solutions, making sure that we generate enough patterns for each subscriber and that each product has enough patterns. We dynamically adjust the objective function. We first use the objective that corresponds to the maximum amount of units we have of each product, and then we dynamically adjust that objective based upon how often we've used the pattern. The idea here is that we want to incent diversity in the products that are used in the patterns, not just generate patterns with most products, but make sure that we get nice mixtures of all the products, and this modification of the objective accomplishes that. The next step is the relax step, and this is based on some work that I did close to 30 years ago, where we created the sifting method for solving a problem that had at that time, 12 million columns. The idea here is that we're solving the linear programming relaxation of the restricted master problem, and we're going to do that using Gurobi's deterministic concurrent optimization. What that means is that we use the barrier method, the primal simplex, and the dual simplex all in parallel. We have a basis if we've solved it once, and whichever method solves fastest is the one we take the answer from. So that allows us to say sometimes barrier will win, even if we have an advanced basis, we don't fix it. Another aspect that comes from sifting is that we remove the non-basic variables and associated patterns that have negative reduced costs, and we add duals from the right constraints to compute a value pi hat. We use that to add back previously deleted patterns as in the sifting method, and then we adjust the objective function. And this is really key. The problem is dual degenerate, which means we get a lot of dual variables that are equal to 0. That means that they would never be included in patterns that we generate. So this formula here uses the amount of unused inventory for that product and adjusts the dual variables to create the objective function for the subproblem. This helps the overall linear programming part converge quickly. And we stop this LP set, the relax step, when the restricted master problem objective is equal to the number of subscribers. The next step is the populate step. Here, we first create the MIP version of the RMP. We don't include all the variables from the LP relaxation. We choose all the patterns first that were included in the LP relaxation solution basis, or patterns that are assigned even fractionally to a subscriber. Then for each pattern, we make sure we have enough subscribers per pattern. And for each product that had a minimum value, we want to make sure that there are enough patterns that include that product. And then for every subscriber, we want to make sure there are enough patterns per subscriber. So the idea here is that we've got these patterns of box configurations. We want to make sure we have enough eligible subscribers per pattern. We also want, for each subscriber, want to make sure they have a lot of patterns to choose from. The overriding goal here was try to not to make the MIP version be too large. So we found that hitting around 300,000 variables typically worked well to make the MIP solve quickly. Now, when we solve the MIP form of the restricted master problem, we can stop under a number of conditions. One condition could be that the MIP is able to prove that as we're maximizing the number of subscribers assigned, that you can't get that number of subscribers via cuts or what have you. Another possibility is we actually hit the number of subscribers. If that's the case, we can stop. We don't need a proof of optimality. We've hit our goal of assigning every subscriber a box. We also found that if Gurobi started branching and did some amount of branching that we weren't improving solutions, we would stop the optimization at that point. In the first and third case where we stopped the optimization, we have not hit the ability to assign every subscriber a box, we first add back all the deleted patterns that we did in the populate stat and go back and solve the MIP again. It'll be larger, but maybe those additional patterns will help us find a solution. And still, the next step is we've now generated these patterns. Suppose we still can't assign every subscriber a box. Remember, we could do it in the linear programming case. We just can't do it in the MIP case. In this case, we generate new patterns and we create these surrogate dual values that are based upon the remaining inventory of the product. What this does is it incents patterns to be created that are going to include the products that we are using almost all of. We want to use those products more and get diverse patterns so that we can still use those products but mix them with other products that come from other patterns. The next steps of the RIP algorithm are the boxes and product step. The first step in the boxes step is to add the constraint that says that we know that we must have every subscriber with a box, and we know this constraint is feasible because of the prior step. In the hard option, we included the constraint that says that there's a limit on the number of box configurations that we can use. So we can skip to the product step. In the soft option, we minimize that sum, looking to, and stop as soon as we hit our target. And then we add the constraint that was in the hard option that constrains the number of box configurations that we will use. And then we go to the product step, and this is to minimize the violation of product minimums. We can stop if that's optimal. A lot of times these minimums were 0, in which case we were done. The user can also terminate, and what we do is we print out what's happening and which products we're not able to satisfy the minimums for, or we can stop after 100 nodes of branching, since we typically found that new solutions were not improving, and it was just about moving the lower bound of this objective. We take advantage of parallel MIP in 2 ways. One way is we use all the processors of the machine on one MIP of the restricted master problem. The other way is to use Gurobi concurrent optimization. In the case of Gurobi concurrent optimization, the idea is that if you change the random seed for Gurobi, it will change the path. And this changes what the Gurobi heuristics will work in terms of finding feasible solutions. So now we basically solve the same MIP in parallel with different options, different random seeds. So we do this in one of 2 ways. One is we use all 24 cores, all on one MIP, or we do this with 6 parallel solves, each using 4 cores, where the difference between the solves is on the basis of the random seed. Now let's take a look at the computational results. There's a lot of numbers on this slide, so let me explain what's happening. Our old solution times are shown on the right here. For the first problem, it was 48 hours, second problem, 17 hours, and we had a simple test problem that was solved in a few minutes. We didn't bother solving the other problems because they take really close to 48 hours to solve, and we didn't have all that computation time available on Birchbox's hardware, which was being used for production work as well. There, at the top are when we use the concurrent MIP option. On the bottom is when we use the default MIP option. We also look at the cumulative time that occurs when we solve the linear programming part to get all the subscribers assigned, the MIP part to get all the subscribers assigned, how long it took to get make sure we hit the number of boxes, hitting that minimum, and then finally the total time, which includes the final objective. In green, in each section, is whether the hard or soft option was faster, and in red is whether the concurrent or the default was fastest. So if you look in the final column here, out of our 7 problems, 3 times the hard option was best using concurrent MIP, but 4 times the hard option was better with default MIP, and 1 time the soft option was better, and that was the hardest problem that we solved in our test set. You'll note that the key time here is on that first problem. A problem that was taking 48 hours is now being able to solve in 19 minutes. We also have applied the RIP algorithm onto some nurse rostering benchmarks that are in the public domain. In this case, there are 24 instances, and for all of them, they have tracked what is the best known solution and whether it's been proved optimal. We found the best known solution for all 24 instances. We've proved optimality for all the problems where optimality had been proven before. This is all typically done in under an hour. We found for one of the instances a new provable optimal solution, and we found a new lower bound for another instance, and we proved optimality for it. And then we found a best known feasible solution for a third instance. So the RIP algorithm can not only be applied to the methods that we've talked about here for solving a Birchbox problem, but here in a totally different problem domain. I'd now like to talk about the novel contributions that we've made. One key is that we're using the MIP solver to generate the patterns in the subproblems. A second is that a restricted master problem that is growing both in the number of columns and the number of rows. We're modifying the dual values in the linear programming phase to improve performance, using surrogate duals when we're doing the MIP in order to generate more columns. And of course, we take advantage of a lot of the powerful features of the mixed integer programming solver in order to improve performance. I'd now like to turn it over to Dave Bendis, who's the Vice President of Global Business Technology at Birchbox, to tell you how this has impacted Birchbox operations.
Not only is the RIP technique something that is abstract and applicable to a lot of other problems, but it's also created real value for us here at Birchbox. The speed and flexibility is really life-changing, and it allows us as a business to take what was weeks spent on creating a valid assortment of boxes, and now that we can do that in minutes or hours, that week plus of time can be spent delivering a more impactful and more personal customer experience. It's also been especially impactful during COVID when our supply chains are a little bit more up in the air, and we can experiment with different things as products are coming in and out. and know whether they will work or not in minutes again, as opposed to weeks.